So the first thing you should do with questions like this is to basically have a good think about the context. Here we have Caroline carrying out an experiment to measure the variation of water depth d with wave speed. So that means she was probably looking at a tank of water which had a slope, and so the water was varying depths. And of course, because of friction along the bottom, the speed of the wave is very much affected by the depth. You don't need to know the context in much detail, but it is important to visualize it. So you know that there's a depth, d, okay, and a speed, and they'll outline how she calculated that in a second. So here we have her results. The data is shown plotted below. Now, the question asking about the line of best fit comes along later, but I'm going to do that now that the graph is here in front of us. It is impossible to do a line of best fit, so what you should be doing is trying to go through all the points as close as possible to the points, and it doesn't matter what position you take. It's really difficult to include this one. I think you might be able to just about get a line of best fit if you get rid of one dot, but you're not actually allowed to do that. And that means that this must be a curve. So if we have a look at what a curve would look like, and you should have been able to draw a curve of best fit which pretty much comes very, very close to all the points. Okay, so this is probably the trickiest one I've seen. Usually when you have a curve of best fit, it's clearly a curve. This one could be a straight line. It could be a straight line best fit, but you have to sacrifice one of the points, and you shouldn't do that unless you have a very good reason to. So what other information did they tell us? They tell us that the uncertainty in water depth d is too small to be shown, that uncertainties in the measure of the water wave speed c are shown as error bars. Okay, so we've got some values there, except for the data point corresponding to D15. Now later you will actually be asked to draw an error bar for D15, so I'm going to do that now because it's here in front of us. Now the question tells you that the error in speed for D15 centimeters is equal to 1.3 centimeters per second. So the first thing you must do is just have a quick check that the units are the same. Yes, they are, so they're not trying to trick you there. And then you go and find the point, which is here, and you measure off 1.3 either way. Okay, so your error bar will kind of look like this. Well, I've tried to do this a few times, it's a bit of a nightmare. So what you should be able to do, it's very tricky on this screen, is you should have a error bar which goes up approximately 3 small squares that way and 3 small squares this way. Okay, so 1, 2, 3, 1, 2, 3, because that would be equivalent to 1.3 centimeters per second. And now we have an uncertainty problem. So if Caroline calculated the wave speed by measuring time t and the time t to travel is 150 centimeters, okay, then what she's doing is she's calculating speed by doing distance divided by time. All scalars. Now remember that this is the wave speed for each depth of water. So the depth of water that we're considering is 15 centimeters, and the speed would be equal to the distance, 150, divided by the time, 8.3 seconds. So that would give us our value of speed, which is important. So we're going to do that first. And that would give you a speed of 18 centimeters per second. Okay, now let's have a look at the uncertainties. We are dividing distance over time, So we're going to have to add the percentage uncertainties of each quantity. Now the percentage uncertainty for distance d would be 2 centimeters over 150 times 100. Okay, which gives us a percentage uncertainty of approximately 1.3%. Similarly, if we do the same for time, the time t is 8.3 and the uncertainty is 0.5. So the percentage uncertainty would be 0.5 divided by 8.3 times 100. And so our percentage uncertainty here would be about 6.02. I'll round up at the end. Okay. Now you must add these two percentage uncertainties because you are dividing the quantities. So when you're dividing and multiplying quantities, you add the percentage uncertainties and you get a total percentage uncertainty of 7.35%. So the last part is simply to work out 7.35% of 18. You plug those values into the calculator and you will get 1.3 centimeters per second. And now is where you try and round up to the best and most appropriate significant figures, which is 2. So the next question is to draw the line of best fit. We've done that one. Tick. And now we can talk about whether the data supports the hypothesis. The hypothesis is that wave speed c is directly proportional to water depth. So the first thing to do is to state what proportional means. This is a very common question. If c was proportional to d, you would end up with a straight line graph through the origin. Okay, and you have not got that. You should remember that we did our line of best fit and we've got a curved line. And a curve is not a sign of proportionality. Okay, so that's pretty much the same question that you saw on the other two, the other pack and the other two questions there, asking you what proportionality actually looks like. This is a nice question about linearization. Another student proposes that c is proportional to d to the power of a half. Draw a suitable graph that can be plotted. Just state a suitable graph. Well, if we linearize this, if c was proportional to d to the half, then we would put c on the y-axis and d to the half on the x-axis, or the other way around. Another option would be to square both, and we would end up with c squared proportional to d, and then you could put that on the y-axis and d on the x-axis. There are some other ways of doing this involving logs, but we're not going to worry about that until later on this year. There is a systematic error in Caroline's determination of depth. State what is meant by a systematic error. So that's a simple definition. It means that we have the same error in every reading. Okay, so we're consistent by a consistent amount. And then state how graph in C would indicate that there is a systematic error. Well, this is a nice question. If you are dealing with a proportional graph, because that's what they're talking about in C. If we go up to C quickly, C, we're talking about a graph of C proportional to D to the half. So you've linearized it, you've come to a conclusion about what to put on the Y and the X, and what it should look like in the end is something like this. Oops. Through the origin. Okay. Now if there's a system, how do we know it goes through the origin? Because it's proportional. Because if Y is proportional to X, it must go through the origin. So if you have a systematic error, then you would get an intercept, you would end up with y equals mx plus c. You would have a plus c value. Okay, so that's the first question.